Are you good?
I'm good. I was good.
All right, thank you for coming out, everyone. This is the info session for Rocketry at Virginia Tech. If you see someone frantically come in a couple seconds, that is the other co-captain of this team. I'm Hannah Cruz. I am one of the co-captains, and these are the sub-team leads of the team. We will be telling you just more information about what we do as a team and some of our sub-projects. Go ahead, Gabe.
Yay!
Just leave it. So, pause it.
Hit the pause.
We are a competition design team. We compete annually in the Spaceport America Cup in Las Cruces, New Mexico. What we're about to show you right here is a video from back when we competed in 2018, because it's a really cool video, and I guarantee if you get on this team, you will watch it no less than 10 times before you leave. All right, so that video you just saw, the rocket was called Whipsnake for our 2018 competition. We've been competing in Spaceport America Cup since the 2017 competition. Here are some quick stats about the vehicles that we've launched in each of those competitions. I'm not going to read off of all of it because I realize it's a lot of numbers. Last year and the year in 2020, the competition got canceled because of the COVID-19 pandemic. And this last year, it similarly got moved online. Also because of the pandemic, but we still submitted our technical paper for review, and we ended up getting first place in our category and fourth place overall in terms of the competition. Go to the next one. These are the pictures of each of the vehicles that we've launched. Some quick stats about each of them. The two on the left are 6-inch diameter. This one's an 8-inch diameter rocket. These two were made with custom carbon fiber body tubes. That one on the left was made out of fiberglass. But what we're doing for this year's Spaceport America Cup competition, we will be competing in the 10,000 commercial off-the-shelf category, which generally means that our motor will be commercially bought. The goal of the competition is to reach 10,000 feet as closely as possible. And then we also have a couple of sub-projects that we're going to be aiming on either integrating into the rocket or continuing development on the side, but our sub-team leads will tell you more about that. And I'm sure they're the ones you're probably going to want to talk to. So, Gabe, if you go ahead to the next slide. Sub-team leads, you've got the floor.
All right, hello everyone. I'm Jack Briggs. I'm a senior in aerospace engineering, and I am the Aero Structures sub-team lead. So what Aero Structures does is we design the launch vehicle. So that includes the body tubes, the nose cone, the fin, and the thrust structure. We perform some structural analysis on pretty much the entire rocket. We do some flight simulations. We manufacture the entire rocket in-house. It's carbon fiber layups using power tools, 3D printing parts, whatever's needed to make what we want. We test those parts that we make, whether that's load testing or destructive testing, and we work to integrate the other sub-teams' systems into the launch vehicle. All right, so as a member of Aero Structures, these are things that you might be tasked to do. We do a lot of CAD modeling. We use SolidWorks. So basically what that entails is we put everything that we're going to build in real life into SolidWorks and put together the entire rocket. We develop and run tests on the structure, so you might be tasked with coming up of a way to test the structural integrity of the thrust structure. We perform a little bit of FEA, especially when it comes to mass optimization, just trying to make things as light as possible without screwing up the loads that they can handle. For simulations, we use OpenRocket. We work closely with the other sub-teams because we have to integrate their stuff into ours, so you might be tasked with communicating with one of the other sub-team leads to figure out what their specifications are to put their things into our rocket. And the big one is lots of hands-on work. Like I said, we manufacture everything in-house, so we spend a lot of time in the lab building various parts and then eventually integrating the other teams into our launch vehicle.
Hey everyone, I'm Mike. I'm a junior in electrical engineering, and I lead avionics. So what we do in avionics is that we handle a lot of the more electronic subsystems for the rocket. So for example, a couple of the important ones include telemetry, which we use to transmit live GPS data and information from the rocket during flight to our ground station, so we can monitor the rocket's health and its position. Something else we work on is the ADS, or active drag system, which you can see a video of us up there working on a prototype of, and a CAD model of it to the left. Now what that does is that it unfolds those fins during flight to add a deliberate amount of drag to the rocket, so we can control our altitude and stay within that 10,000 foot range. And we also work on all these other systems and projects bulleted down here, as well as anything we can think to make the rocket more electronically sophisticated. And so to do our work, we use a lot of these skills and processes bulleted down at the bottom. So a lot of these are electrically inclined, so we do a lot of work with circuits, microcontrollers, programming, wiring. We're looking to get more advanced with our work going forward with making custom circuits and PCBs. Although we're not just electronically restricted on our work, we do a fair bit of CAD and modeling too. So, for instance, the ADS is a complicated moving part. So if anything of what I just said sounds of interest to you or cool, definitely feel free to talk to me after the meeting or go ahead and email me.
Hi, my name is Carmen White. I'm a junior in physics here. I am the lead for business and public relations. So what we do is we're essentially the spokesman for Rocketry. We do a lot of actively scouting for sponsors and business partners, as well as working on a sponsorship package that we send out to ask for money. We go towards our funding. We also do a lot of photography, video, and graphic design for ads, posters, flyers. Anything you see submitted is what we work on. We also actively keep up with social media, and so we have Instagram, Facebook, and YouTube right now that we hope to expand on. We do outreach events, and previously those have been held online or in some form different than how they were in the past. We had the Kids Science Festival, as well as the other one there. We had to actively work with the community and children, and then we do team events as well. So those have also been on Discord and online through the COVID. But we had one that was a cookout. It was really fun to get everyone involved and all the teams together, and not just you're just left to your one team. We all got together, mingle, talk. It was a great time. So we're hoping to do more of those once we get started this semester. And then we also do merch, so like the t-shirts, business cards, standees that we send out to our business partners. Anything that's like artistic and creative and graphic with Rocketry we work on.
I'm Griffin. I'm a junior in aerospace engineering, and I'm the lead of design validation. So basically what we do is a lot of analysis for all the other sub-teams. And we're split up into two parts, FEA, which is like structural analysis, and then CFD, which is fluid analysis. For FEA, we analyze a lot of the different subsystems, including the active drag system. We just make sure that they can withstand all the loads during flight. We work on the hybrid motor development, analyzing the oxidizer tank pressure and the motor test stand that we do all the testing on. We just ensure that it can handle all the loads. And then any structural analysis for the body that Aero Structures needs us to do. For CFD, we also work on the active drag system. We look to see how much drag is produced by the active drag system to help us reach our 10,000 foot goal. We look at rocket stability because that's one of the major requirements. We work on optimizing components, so we sort of work closely with the design of the rocket to help reduce the drag and maximize the structural integrity, as I mentioned before. And then we're also looking into doing wind tunnel testing, which can also help us validate our results.
Hi, I'm Neha. I'm a junior in aerospace engineering, and I'm the lead for Payload. So why do we launch rockets? The answer is to deploy payloads. So our goal on Payload is to build something cool, or as the SEL Payload Challenge calls it, something of scientific or technical value. So how many of you went to the football game, the UNC game? So did you guys see those skydivers coming down to the ground? So that's what we're trying to do on Payload. We're trying to steer our CubeSat that we eject out of the rocket to the ground autonomously. So to do this, we integrate our system into the rocket, so we work closely with a lot of the other sub-teams. We do a lot of energetic testing, and we have custom live video and telemetry systems on our CubeSat payloads. So here you'll see a video of an energetic test we did last semester.
Is everyone ready?
Yeah.
Okay. 5, 4, 3, 2, 1.
So how we do what we want to do. So this is a lot of designing systems and parts, a lot of problem solving. So you'll be doing CAD and electronics, and the whole summary of what you're going to be doing on Payload is designing, building, and testing. And then based off of your tests, you start all over again, redesigning, rebuilding, and testing again. So we've got a lot of microcontrollers and circuits. We've got physical parts that we build and test. So we do a bit of everything on Payload.
Hey guys, my name is Ben Piper. I'm a sub-team lead Propulsion alongside with my friend George here. We're both juniors in aerospace. This is a picture from one of our tests last year. Go ahead. So I'm going to talk to you guys about what Propulsion does. We are, alongside with the rest of the team, designing a hybrid motor. And while the rest of the team is building their rocket that will be flying this year competition, we're designing and manufacturing this motor to fly in the rocket next year. So what is a hybrid motor? It's pretty simple. Well, not really. You've got your liquid component and your solid component, and that's what makes it a hybrid. So the liquid is nitrous oxide for us, as you can see in the diagram. And then our fuel grain, we use ABS 3D printed plastic. And so when you open the valve, the nitrous flows in, you spark it, and that's where you get your combustion from. And that's how a hybrid motor works in theory. So what would you do as a member of Propulsion? We do a lot of CAD, just like most of the other sub-teams. You can't really get away from CAD on Rocketry. We work with a lot of electronics to control our motor. We use motor controllers to open most of our valving. So we love electrical engineers, just like most of the other sub-teams. We do a lot of stuff with Arduinos and BeagleBones, and we manufacture a lot as well. So you kind of get we're kind of a jack of all trades team. We work very closely with software and a good amount with Avionics to integrate all of our stuff. And the goals for this year is a cold flow and static fire testing, and what that means is a cold flow is where we flow all of our nitrous through our tank and out of our nozzle, or out of our injector plate to get our mass flow rate of our engine. And then a static fire is where you then connect that to our fuel grain and spark it, and we get fired. And a lot more. Those are our goals for this year on Propulsion.
So he mentioned software. I'm the software team lead. My name is Benay. What do? We create the software that controls the hybrid motor components. We create software that reads data from the hybrid motor. We don't want unknown pressure values inside of our pressure vessel, because then it leads to things exploding. They don't like things exploding at Kentland. We also work with Prop to create the circuits that are controllable using a BeagleBone Black. That's one of the things he mentioned earlier. We're potentially thinking about making it wireless this year. It adds a little bit more complexity to the system, but it also adds a little bit of ease in terms of like installation and things like that. We also develop and deploy our network system. That little antenna-looking thing you see there is an antenna. Well, and if you guys can see, I don't know if you can, there's a little black dot. That's a car very far away with another antenna, and that's sort of the distance that we used that network system in our cold flow last year. And then we're also a general software expert group for just like the other teams if they need any help with any specific things. And we're also working with business and PR to maintain our website, make sure it's up to date. I think last year we updated it in the spring, which is not what we want. We want you guys to be able to go on the website and see what we're doing, see cool pictures, stuff like that. How do we do it? Commercial grade antennas. That's an antenna. It's made by this company called Ubiquity. These antennas are the sort of antennas they use in like New York, when they're trying to connect two buildings to the same network. So it'll be two skyscrapers and they just sort of beam the network across to each other. We use BeagleBone Blacks. These are essentially Arduinos, but on steroids, sort of. We use something called Robot Operating System. Sounds cool, right? Right? Most of the industry uses this for like autonomous systems, things like that. It's using Python, so if you don't know that much programming yet, you're fine. It's Python. I can teach it to you like right now if you want. We're thinking of doing some custom-made circuits, possibly working with Avionics or with Propulsion to do that. Generally, when you think software, you should be thinking less Facebook, Amazon, Google, and more like Boston Dynamics, Tesla, that sort of stuff. Not, point and click does things. Hey, Ben, what's a cold flow?
As I mentioned earlier, a cold flow is where we flow all of our nitrous oxide through our tank and through our injector. And so here's a video of that test from last year.
So to give some quick context before it plays, that building over there to the right is roughly how far we are. And this is a GoPro sitting on a little box. And you'll see it. Go ahead. It's a lot of that, yeah.
The video's the rest of that. You're not missing anything.
Cool line twist.
No. No.
Alright, my turn. So, what goes up must come down. My name is Gabe. I'm in charge of the recovery sub-team. The objective is to bring the rocket down, keyword, safely. So that involves parachutes, parachutes plural. The term is dual deploy. So if you look right here, here's a diagram of like a typical model rocket where you just have one parachute that comes out right at the peak of the flight, and then it drifts like forever, and you have to walk for ages to go and find it. What we want to do is have multiple parachutes come out. So a tiny one comes out at apogee, called the drogue chute. It falls most of the way, and then a big main parachute comes out at a lower altitude, like between 500 and 1,000 feet probably. So this is kind of the setup that we want. And how do we control that? Via more electronics. Specifically, this is an example of a flight computer that I put together. It's a kit. So there's a barometric sensor. So reads air pressure. That basically tells the altimeter how high it is, and then it'll set off black powder charges. So that's the basic scope of kind of one of the systems that we'll be working with. So if you're on the team, you will be selecting, programming, integrating, and testing recovery electronics. That means picking like what kind of electronics we want. If we want a barometric one, or if we want like just a dumb timer, and figuring out all the redundancies there. And then integrating it into the rocket, like everybody else said, like a lot of CAD, working with the other sub teams, like Aero Structures and Avionics, to integrate everything and put it where we want it in the rocket. And then testing it. So testing it when it's outside of the rocket, testing it when it's inside the rocket, making sure everything works, because these control our parachutes. And that's like the brakes on the car. It's like the most important part, I think. Sizing and testing the black powder charges and parachutes, that kind of goes along with that. We want to make sure that the black powder charges that eject the parachutes are big enough, but not too big to tear everything apart. So a lot of not destructive testing, but like ground testing the black powder charges and making sure it pops the airframe apart on the ground. Sizing the parachutes for proper descent rates, and then we'll work a lot with Avionics to kind of work on the crossover between Avionics and recovery there, especially with GPS and Avionics. Yeah, so that's my sub team.
All right, I know this is probably now what a lot of you care about. What we're looking for next in the application process is that we will be sending out an email tomorrow at 5 p.m. to let you guys know that the application is open. We give you a little bit more than a week to fill the whole thing out. And keep in mind, we also will mention it in the application, but be sure to send us your resume. We need your resume. But at the same time, also do not be intimidated if your resume perhaps is not perfect. My resume had like a grand total of maybe 5 bullet points on it when I submitted to this team.
Who was a lead at like freshman level had a good resume, you'd say? Don't worry about the resume. Answer the questions as best you can. They'll be like engineering-y questions. They're not like too complex. I talked about a lawnmower in mine. It's not that bad, guys. Don't stress too much.
And then our estimate is the 22nd to send out offers for interview applications, but we'll also keep you guys up to date just in case anything changes and for further updates in terms of interviews and applications. And then before I set you loose to talk to the sub-team leads, which I know you probably want to do, I hope that after listening to this presentation, you guys think that a lot of these cool projects and you're excited to work on them, but I don't want any of you to be worried about like, no, I don't know if I have the bandwidth to do this. Like, I don't know if I've got the experience, because when I joined this team, I had no idea what the word apogee meant, and none of you should be ashamed if you don't know what it means either. This team is a good opportunity for learning. We know that some of you may not have very much prior experience, but also what we're here for is to help you learn, to give you an opportunity for a hands-on experience. And then lastly, before I send you loose, we are keeping track of who is attending this info session so we can send you these slides afterwards so you have this information. So if you have not yet swiped your Hokey P on this neat little thing that I got from the source, please come up here and do that. In terms of questions, if you have any general questions, you can come up here and ask me. You can ask my other co-captain, Zach, in the orange there. Say hi, Zach. And then we'll have the sub-team leads spread out around the room. If you guys could shout out your sub-team so people can remember what the heck you guys do, that would be great. Thank you all for coming, and spread out.